Okay, so last time we started talking about vector fields. That's what we're going to pick up today. So let's just, what's the idea here? The vector field is the idea that every something in a coordinate system has a something associated with it. So a vector field is a type of function, right? It's a type of function, and so the independent thing is the first blank, and the dependent thing is the second blank. So every what in a coordinate system has a what associated with it. Yeah, what's that?
Point vector.
He wants point. He says every point in a coordinate system has a vector associated with it. Agree with that? Yeah, point, or we could say location. Yeah, so every location or every point in a coordinate system is assigned a vector. So that's the idea of a function, right? So the components of the vector are determined by the location or by the point. So each of the components is a multivariable real valued function, right? Because you're going to take the values of the coordinates and the x component will be a function of those coordinates, and the y component of the vector will be a function of those coordinates, etc. So what does that look like? That looks like, in R2, that looks like this. So is this a real valued or vector valued function? Vector values. Vector fields are vector valued function, and is it single variable or multivariable? Multivariable. So that's what vector fields are. They're vector valued multivariable functions. Every location x, y determines a vector, and that's by each component having its own function of that location, and then you get a vector out of that. And then in R3 it looks like this. So this is a vector valued 3-variable function. Okay, so we looked at the first example last time, and let's actually figure out what that was. Okay. All right, so you're going to make I'm going to give you locations, and let's zoom out once. Okay, so here is the location 0, 1. So 0, 1 is like the value of the independent variable, right? It's the two coordinates 0, 1. And what vector do we get for the point 0, 1? What vector do we get? We get the vector 1, 0, right? 1, 0. So write that down. So make a table. So you're going to make a table, and you're going to figure out what this vector field is, right? So your first clue is that the point 0, 1 is assigned to the vector 1, 0. Okay, here's another clue about what this vector field is. So you're the detectives here, and so given this information, you're going to put together all your clues and figure out what the vector field is. So here's the next clue. Did you write it down? You got it? Check with your neighbor. Make sure you agree with your neighbor on this one. Check with your neighbor. Make sure you got it right, everybody. Just what you're looking at here. That's all I'm saying. Just what you're looking at here. Okay, ready for another clue? Here we go. So here is here's another clue. Write it down. Right? Location, vector. Location, vector. That's what a vector field is. Every location has a vector assigned to it. Got this one? Quick. We'll do one more, and then, what was the first one we did? What was the first location? 0, 1. Okay, so we'll do 2, 3, 0. 2, 0. Okay? Here's a location and the associated vector to give you another clue at what this vector field is. So now you're going to look at all the locations and associated vectors and write down what the field is. So what will that be like? That'll be like, this is a two-dimensional field. So you're going to write given a point xy, given any point xy in this plane, what is the associated vector to the location x comma y? John thinks he's got it. Jorge, do you think you got it?
The associated with what?
So what is the vector associated with a generic point x comma y? Okay, take a look at your list, and if you haven't figured it out yet, figure it out. So Christian's got it, John's got it. Jorge, what were your lists for your locations and vectors?
So my points were 0, 1.
0, 1, and what vector did you get for that?
1, 0.
1, 0.
And then 2, negative 1. Negative 1. Negative 2.
Okay.
And then negative 2, 2. And then this one I might have got wrong, but I got negative 2, 2 again. Or positive.
People are saying it's 2, 2. Okay, and what's the last one?
2, 0. And then 2, negative 2. 0, negative 2.
Okay, so now we look at the pattern, right? 0, 1 gives 1, 0. 2, negative 1 gives negative 1, negative 2. Negative 2, 2 gives 2, 2. And 2, 0 gives 0, negative 2. So how are we getting the components of the vectors from the x and y coordinates? Yeah, Jonas.
So your x component of your vector is just going to be y.
The x component vector, is it always y? Yep.
The y component of your vector is negative x.
And the y component is the opposite of x. Agree? Anyways, for those four, right? So that this wouldn't be conclusive proof, but it's a lot of evidence, right? We got 4 different locations and corresponding vectors that seem to point at the vector field y, negative x, right? So it's taking the coordinates x, y, and forming an associated vector with every point x, y, according to these two. That the x component is the y coordinate, and the y component is the opposite of the x coordinate. So all that together looks like I showed you this last time. So this is then a view of kind of the whole field. This is the field, what? Y, negative x. Y, negative x. Okay, and so if I were to show you every vector, it would look like this. So we don't show every vector because it doesn't show us anything, right? So you just show like a grid of them to get a feel for what the vector field is like. So the length of the, just like vectors we learned at the beginning of the semester, length of the vector is symbolic of the magnitude, right? So the relative lengths of the vectors are showing relative magnitudes of those, okay? And so if I took away the magnitudes, let's see, it would just show the directions, right? So this is showing all the vectors of the same length, and it's just showing kind of the direction at any point. This shows direction and relative magnitude of the vectors in the field. All right, let's do another one. We got the hang of it. Okay, here's your first clue. So I'm giving you a location and the corresponding vector. So the location is always at the tail of the vector, so I'm putting the tails of the vector at the location, and then you got the corresponding vector. Everyone got that one? If you need to check with the person next to you, that's fine. Okay, here's the next one. So what is our goal? Our goal is to, there's a vector field here. I'm going to give you little clues, and you're trying to figure out what the vector field is. Okay, got it? Think you got it? Here's another location and associated vector in this new vector field. This is a new vector field.
Wait, this is totally different.
This is a new vector field, and this is the third vector I've shown you in this new vector field. Is it different? It should be different. Are they different? Okay.
Yeah.
All right. Let's show that. So what locations have I given you so far? I should write those down. 2, 0.
1 and 2. -1, 1. -2, 0.
All right, I'll give you one more here. How about, you okay?
Yeah.
All right, -1 and -2. How about? All right, wait a sec. -2, 2. There we go. -2, 2. Okay, see if with those 5 points you can figure out what the vector field is. Work together if you need to.
Did you mean to do -2?
This is what I meant to do. -2, 2. This one.
Instead of -2, 0.
No, I did -2, 0. I can show that one again if you want.
Yeah, can you please?
Sure. So let me just wait a sec for this. This is -2, 2. And here's -2, 0.
Oh, I thought. Okay, thank you.
Sure. Any requests to show one again? Anyone want me to show any of those again? The first one, 2, 0. There's 2, 0. All right, I'll give you one more. Or let me tell you, what do you think 0, -1 should be? Anyone have a guess? What do you think 0, -1 should be? Yeah.
It should be 1, 1.
He wants 1, 1. If I do 0, -1, he's right. Okay. How many people think they got it? Okay, just take another minute. So you're trying to figure out what the x component is and y component based on the coordinates. Are more people getting it?
I thought it was well, I thought it was plus x minus 2y, but it's not working.
Okay, yeah, it's a little easier than that. Alexandria, did you get it? X component? What's that? X plus 1. X plus 1 is the x component. You take the x coordinate and add 1, you get the x component. All right? Did you get y? What did you get for the y component?
Negative y plus x.
Negative y plus x, or x minus y. Does it work? Is that what you guys got? I see lots of nods. Good. All right, so let's take a look at that one. So what does that vector field look like as a whole? Kind of looks like that. So near 0, you get relatively small vectors. You get away from 0, the vectors get larger. If we just want to see the direction of it, oh wait, that's not the right one. Where is it? It's purple. Where is it? That's weird. This isn't right. What was it again? X plus 1. I changed it. And y minus x.
X minus.
Sorry, x minus y. Ah. There we go. That's what it should look like. Okay, so most common, or maybe the most obvious application of this would be like flow fields, right? Can you imagine like a channel of water and it's measuring, this is around Florida, it's like the Gulf Stream, right? The Gulf Stream's like the direction and magnitude of current, right? Where the vectors are long, you have strong currents. Where they're shorter, you have relatively slower currents. Okay? And then the direction is pointing the direction of flow. Same here. This is the English Channel. Yeah, between England and Europe there. Again, flow field. And then also there's like wind, right? So here's wind flow. Again, magnitude of the vector, it would be the speed of the wind or strength of the wind. Direction, it's just pointing the direction of the wind. It says February, but our February was pretty windy. This is showing not too much wind in Phoenix here, right? The vector's really short. But there was a lot of wind in February, so I would think this would be like July in Arizona. Right? Okay, but another one is magnetic field. Yeah, no, that wasn't this year. So here's this is a magnet, and so this is showing the magnetic forces around the magnet. So you have the strongest forces close to the magnet. As you move away, the forces decrease, and then you have the repulsive side, right? So that's, and then the attractive side would be the blue side. And then when you're close to it, you have the strongest magnetic forces. So these are examples of flow fields, that there's a vector associated with a location, right? Vector associated with location. All right, so let's try some harder ones here. 3D. So every 3D coordinate, well, actually, we didn't do these. So let's do this. Why? Where am I? Okay, so now I'm going to give you the whole field, and I'm going to tell you that for each one of these, the x and y coordinates are either plus or minus x, plus or minus y, plus or minus 1, or 0. And you have to figure out what they are. So these are only these vectors don't show true magnitude, they just show relative magnitude. But based on those relative magnitudes, you can figure it out from the fact that I'm telling you that all the components of all these fields, and I'll try to orient them better, but all these components of all these fields are either plus or minus x, plus or minus y, plus or minus 1, or 0. So for instance, negative y comma 1 would be a potential vector field that you could make out of these possible functions. Or negative 1x. That's another one. Or xy. Or x negative x. For the x component, you could pick any of these, and for the y component, you could pick any of these. So you're going to figure out what these vector fields are. Work together. Go. And I'll take attendance. Okay, Sarah, you're first. Take your pick. You get to choose any one you want. Top left? What do you think it is? Y comma x. She thinks the top one is y comma x. And can you say why?
Well, we came up with it because at -4, the magnitudes are larger in what the x direction is.
Okay. So that
it would make the y vector value at the x value the point.
Okay. So the x component, so y comma x?
Yeah.
So the x components of these vectors are the y coordinates. So as you go up in y, your x coordinate gets bigger and bigger positive. As you go up in y in the field, then the x components of the vectors get bigger, and as you go down, y increases negatively, your x components are going to increase negatively. That looks good. And then as you go this way, your y components are going to get bigger positive, and as you go this way, they're going to be bigger negative because x is negative. Agree with this? Y comma x? Yeah, so the x components of the vectors are whatever the y coordinate is, right? So for a high y coordinate up here, you have the largest positive x components. Along y equals 0, the x components are 0. There's no x component. When y is a big negative number, that's what your x component of these vectors is. Do you see it? And then you could argue the same thing with x. Got it. Y comma x. Okay. Let's see. Astrid, take your pick. You have a question or you want to do one?
I was going to do
Okay, you can do the next one. Astrid, take your pick. Bottom right. What do you think? She wants x comma 0. So all the y components are 0. That's good. And then the x component of the vector is whatever the x coordinate is. Look good? Okay, John. You pick. What do you want?
top right is negative x comma negative y.
Negative x comma negative y. Couple nods. Why is it negative x, negative y? Can you explain?
So like, I looked at like the row, like the y equals 1 row.
Okay.
As it goes to the right, it points more to the left.
Okay.
Which means it's like negative.
Right?
And then in the x equals 1 row, as you go down,
Okay.
it goes more up.
So y is more up. As you go up, y is more down. Okay, if you have a question, please stop me. Let's talk about it if you're not sure. So that, yep. That's out of the way. Okay, last one. Chrissy, did you get this one?
You said 1x?
1 comma x. Christian likes it. So why 1 comma x?
Because in like x direction, the vectors all point like positive, and it's like
The same amount,
yes,
right?
yeah.
So you have the same constant x component, right?
And then with y component, it moves with x.
Right, as you move to the right,
Yeah.
the y component gets larger and larger.
Yeah.
As you move to the left, the y components get larger and larger negative.
Yeah.
Any questions? Okay, now for the 3D one. Now that you got the hang of this.
Yeah.
Okay, so now your position in space indicates what? The 3 components. The 3 components are based on, and again, it could be, so now add plus or minus z into the mix. So your components could be plus or minus z, plus or minus x, plus or minus y, plus or minus 1, or 0. You can do it. So I'll just give you different views. Okay? So like here's looking right at the YZ plane. So what component do you not see? So yeah, so you can see by looking at the YZ plane, you can see so I'm just gonna leave it right there. I think a little bit more about this. Okay, I'm just leave it there for a while. See if you can get it just looking at that view right there. Kind of our standard view of the. So you're trying to figure out what the x component of the vectors is, the y component of the vectors, and the z component of the vectors.
Oh wait, no, x is 0.
Are they straight vertical lines? Or are they kind of pointed?
In the Y
Yeah, the slanted direction is the x direction. Yeah. So here's straight on.
Yeah, it's y now.
Oh, it might be positive 1. Wait, for the original. X is 1. Oh, yeah, 1.
Okay, Eddie, any idea? 10Z. They're offering. I see some nods. Offering up. So why 100? The x component is 1 because So this is the xz plane. This is x to the right and z up. So always a constant x component. Y component is 0. And then z is whatever the z coordinate is. Do you see? Does it make sense? You have these in WebWork, so I want to give you some practice. But this is really good. They're super good problems for like understanding what a vector field is, because you really have to work at, okay, if the location is here, the vector is here, right? So it's all about that each location is determining a vector. 1, 0, 0. All right, let's do another one. It's slightly harder. You can do it. Okay, so here's the deal. The vectors in front are the ones that are closest are the most pink, and the ones that are furthest away are the least pink. Okay?
So the Z has
Yeah, the Z axis is changing. So Z has to be.
Here's coming up on the XZ plane. Here's coming up on the XZ plane.
Wait, it's because it changes, as it changes.
X to the right, Z up.
X to the right. So it's oh wait, so
Y would be
so as X becomes positive, X gets yeah.
You're right.
Negative.
That's always, yeah, that's right. Yeah. That's for negative.
Y is zero.
Okay, here's the XZ plane again.
But doesn't it when it goes up get smaller? Does it? Okay, now this time
So this is that's the way
Here's the XZ plane again. So what's the Y? What's the Y component? Y component is 1 also?
yeah, that's what I was thinking.
and then
So would we say X is Z? What is X is Z?
is that
That's what I said. I think that's
Y is 1. I thought X was 1 too. Oh, X is Z. Z 1. Z1X. Okay, what do you think the X component is?
Z.
Z, good. What is the Y component? Okay, look at it. This is the best view for that. What's the Y component of all those vectors? The same, positive value, right? So, Y component is 1, and Z component. YX. Yeah.
Why?
Yeah. How come? How come?
Because as you like, you have like a constant Z in that plane. Like as you change the X value, the Z component changes.
You go in the X direction, you increase more positive Z of components.
Negative X, you get more negative.
Right. Let's see. Z1X. Okay, so It's okay if you don't 100% get it, but which is there a component you want to talk about? Which component? Any questions? Don't hesitate if you're not clear on one of the components. Yes, please. Y equal to 1. Okay, so if you look at this view right here, look right at the YZ plane. We're saying what's the horizontal component of these vectors? It's like no matter what, it's the same positive value. Do you see that? Is that better? It's like not changing. The Y doesn't change ever. It's always just to the right, the same amount. Any other questions? Okay, so let's look at this. Remember what the gradient was? Do you remember? Do you remember? What was the gradient? As I promised, everything comes back. Everything comes back. What was the gradient? Do you remember?
Greatest change.
Direction that had the greatest change.
Direction of the greatest change of what? Direction of the greatest change of a surface, right? So we had a multivariable function. We picked a point, and we said the gradient at that point was a vector that pointed in the direction of max rate of change, right? And the magnitude of that vector was?
1.
No. The magnitude of the gradient, remember? Oh, magnitude.
What's the unit vector? What's the greatest?
It was just the magnitude of the y.
No, so that the direction of the gradient was the direction of greatest rate of change, and the magnitude of the gradient was the
Rate of change.
the rate of change, that magnitude of that greatest rate of change, okay? So I want you to find the gradient of the function x squared plus y squared minus 3 at the point -1, 2. So find the gradient, remember how to find the gradient, and find it the particular value at -1, 2. Okay, I need my pen back, so while you're working on that, I gotta get my pen. Okay, how do you find the gradient? I was looking through their notes. Anyone remember? John?
It's the partial respect to x.
Uh-huh.
And the partial respect to y.
Great. It's fx. Fy. So fx is 2x at -1, -2, 4. So this tells us what about the function f at -1, 2? It tells us what is that vector telling us about the function f at -1, 2? Shane.
You follow the direction that will give you the rate change, maximum rate change.
Okay. Yep. So at the point -1, 2, this, if you go in this direction, you'll be heading in the direction of greatest rate of change of that surface, of that function. And what is that rate of change?
The magnitude.
Tell me. Square root of 20. So at -1, 2, the greatest rate of change you could find would be square root of 20, and that would be if you went in the direction -2, 4. Is that a good refresher? Does that make sense? All right, so then, so now find the gradient at any ordered pair. So just not at -1, 2, but just at any ordered pair xy. What would it be? 2x, 2y. So look, it's a vector that's dependent on location xy. Light bulb, what is that? So what is that? So the gradient is a vector field. Do you see that? This is a vector field. Based on location, you get a vector at every location. And so that vector is telling you what? It's a whole field of vectors showing you direction of max rate of change and magnitude of max rate of change at every given point. So this is what we call a gradient field. It's all the vectors, all the gradient vectors make a vector field called the gradient field. So let me just show you this. I'll show you the surface and the field together, and you can see what's happening. Well, anyway, what is that surface? So x squared plus y squared minus 3. That's a surface we should know or be able to figure out. What kind of thing is that? It's a paraboloid with vertex at 0, 0, -3. Opening which way? Opening up. One more thing. Let's see here. And so then the gradient field so which way is direction of max rate of change? If you're walking in this on this paraboloid, which way do you walk for the greatest rate of change? Straight away from the origin, right? So at any point on this surface, if you walk straight away from the origin, you'd be going uphill the fastest. And that's what the vector field shows. You see that? The vector field is in R2, and it's showing direction of greatest rate of change, which in this case is always straight out from the origin. Because that's the vector field 2x, 2y.